When you first began the study of chemistry, you learned that the chemists have assigned to each element a characteristic atomic weight. Now, the determination of these atomic weights is one of the basic processes in chemistry, because the atomic weights of the elements are used in a great variety of calculations in chemistry. Today, we're going to demonstrate how the atomic weight of an element can be determined using the law of Dong and Petit and some other relationships in chemistry. Dong and Petit's law deals with the specific heats of the elements. Now, specific heat is defined as the number of calories required to change the temperature of 1 gram of the substance 1 degree centigrade. And this is a quantity which it's going to be possible for us to determine in the lab. Knowing the specific heat, we can calculate the approximate atomic weight, because Dong and Petit found that when the constant 6.4 was divided by the specific heat, the result was approximately equal to the atomic weight for most elements. You previously discovered that the equivalent weight multiplied by the valence, or the combining capacity, equals the atomic weight. And you also know that the valence of an element is always a whole number. Now, the equivalent weight is another quantity which is possible for us to determine in the lab rather easily. So using these two relationships, it's actually possible for us to calculate the exact atomic weight. First, we'll calculate the approximate atomic weight using the specific heat method. Then we'll calculate the equivalent weight. Exactly. Then we'll determine which whole number, the valence, we have to multiply our equivalent weight by to get a value which is approximately equal to our atomic weight. And that number will be the exact atomic weight of the element. Our first step, then, will be to calculate the approximate atomic weight using the Dong and Petit relationship. And this will require us, first of all, to calculate the specific heat of the element, which we will now proceed to do. The first step in this method for determining the atomic weight of copper is to determine the specific heat of copper. I have a small block of copper metal here which has been placed on the pan of the balance. We're determining the weight of this piece of copper on a rather inaccurate balance, but great accuracy is not necessary at this stage of the proceedings because our determination of the approximate atomic weight of copper is just that, approximate, and great care in weighing would be a waste of time. So the weight of this piece of copper has rather rapidly been found to be 39.2 grams. This weight should be recorded because it will be used later. We must now heat the sample of copper to a fairly high temperature and then also measure that temperature accurately. We've tied a piece of string around the copper so that we can lower it into a test tube. You'll notice that the top of the copper block has a small hole drilled in it, which permits us to insert a thermometer into the copper block. We then place the copper in the test tube, slide it to the bottom with the string, place the test tube in the beaker of water, which we're heating with the Bunsen burner, and clamp it in place. We'll then place the thermometer with the bulb of the thermometer sticking into the copper block. We'll now boil the water and wait until the temperature of the copper becomes constant. While the copper is heating, we'll prepare the next piece of apparatus for the rest of the experiment. In this graduated cylinder, I've measured out exactly 35 milliliters of water. We'll add this to the small beaker. A thermometer, which is graduated in fifths of a degree, has been mounted in the stand, and we will determine the temperature of the water before the copper has been added to it. The temperature of the water in the small beaker is 33.6 degrees. temperature of the copper metal is 99 degrees centigrade. We'll now remove the thermometer and add the piece of copper to the small beaker. The temperature of the water in the beaker is rising, and we will read the highest temperature reached by the mixture of copper and water. The final temperature reached by the mixture is 39.9 degrees centigrade. We can now proceed to calculate the specific heat of the copper from the data which we've obtained in this experiment. We found that our little sample of copper weighed 39.2 grams. We then placed this copper in the test tube, immersed the test tube in the beaker of boiling water, and found that the final temperature reached by the copper was 99 degrees centigrade. We then placed this copper in a beaker containing 35 milliliters, which we will assume to be 35 grams of water. We can note the temperature of this water before we placed the copper in it was 33.6 degrees centigrade. Now the final temperature of both the copper and the water was 39.9 degrees centigrade. Therefore, the change in temperature of the water was 6.3 degrees. This is from 33.6 up to 39.9. While the change in temperature of the copper is 59.1 degrees. This is the 99 degrees down to 39.9 degrees. And with this information, we can calculate the specific heat of the copper, because the specific heat of the copper is equal to the grams of water multiplied by the temperature change of the water divided by the grams of copper multiplied by the temperature change of the copper. And we have all four of these figures. This then becomes 35 grams of water times 6.3 degrees over 39.2 grams of copper times 59.1 degrees. And carrying out the multiplication and division, we find that the specific heat of the copper is determined experimentally to be about 0.095 calories per gram per degree centigrade. And we will use this figure now in calculating the approximate atomic weight of copper. You'll recall that the Dong and Petit relationship is that the approximate atomic weight equals 6.4 divided by the specific heat. Now we've determined the specific heat experimentally for copper, our value being 0.095. And when this computation is carried out, we find that the approximate atomic weight of copper is 67.4. It's difficult to say how accurate this figure is, but it's probably plus or minus 5 or so as an order of magnitude. And this figure will be very useful to us later on in determining the valence of copper. The equivalent weight of an element is defined as the number of grams of the element that will combine with or displace 8 grams of oxygen. Now we're going to determine the equivalent weight of copper starting with copper oxide. Copper oxide, which I have some in this bottle, is a black powder. This is a very finely divided sample here. We're going to weigh out a carefully measured quantity of copper oxide. And then we're going to remove the oxygen from its combination with copper oxide, leaving metallic copper. And by subtracting the weight of the copper from the weight of the copper oxide, we'll be able to tell how much copper combined with how much oxygen, and from that data calculate the equivalent weight of copper oxide. Now the small porcelain boat on the left-hand pan of the balance has previously been carefully weighed. Its weight is 6.6475 grams. 6.6475 grams. This figure should be recorded as the weight of the empty boat. Now to this boat I've added some copper oxide. And the boat plus the copper oxide is now being reweighed. This value is 8.8120 grams. 8.8120. That's the boat plus the copper oxide. So that the particular sample of copper oxide that we're using, the black powder in the boat, weighs 2.1645 grams. And this figure will be of importance to us later on in our calculation. Our sample of copper oxide in the porcelain boat has been carefully placed in the end of the test tube. Here we have a hydrogen generator set up with mossy zinc in the Erlenmeyer flask, to which we've added some water. We're going to add some hydrochloric acid to this flask, and this will cause the generation of hydrogen. We'll add more acid from time to time to keep a steady flow of hydrogen coming from the generator. Now the hydrogen is passing through this tube, through the calcium chloride drying tube, which will pick up any water vapor or spray, and then through this tube to the rear of the test tube. There it will flow over the copper oxide and back out of this exit tube. Now we'll permit the generator to run for several minutes to displace all of the air in the system. We'll also wrap the generator bottle with a towel to prevent the flying around of glass fragments if the generator should explode during the course of the experiment. We're now heating the copper oxide in the tube in a stream of hydrogen. The hydrogen is coming out of this glass tube. We're looking down into the reaction from the top. You'll notice that at the closed end of the test tube, most of the copper oxide in the boat has already been converted to metallic copper. You'll also notice that considerable quantities of steam have condensed into water here in the cool part of the tube. This water is formed in the reaction between the copper oxide and the hydrogen. In a few moments, all of the copper oxide will have been reduced to pure copper, and we'll then let the test tube cool in an atmosphere of hydrogen to avoid any possibility of any reoxidation due to oxygen in the air. After the reaction is completed, the boat should contain only metallic copper formed in this reaction. We've now completed the weighing of our sample of metallic copper in the boat. All of the copper oxide has been converted to copper. We've cooled the sample, weighed it, and found that the boat plus the sample now weighs 8.3775 grams. 8.3775. And with this information, we can now proceed to calculate the equivalent weight, the valence, and the exact atomic weight of copper. We found that our empty porcelain boat weighed 6.6475 grams. When we added the copper oxide to the boat, the two together then weighed 8.8120 grams. By subtracting this figure from this one, we find that the weight of the copper oxide is 2.1645 grams. Then we placed the boat in the tube and heated it in a current of hydrogen, and we found that the boat, after the reaction containing the copper, weighed 8.3776 grams. Now from this figure, we should subtract the weight of the boat to obtain the weight of the copper left, and this is 1.7301 grams. Now if this is the weight of the copper, and we added 2.1645 grams of copper oxide, by subtracting this figure from this one, we obtain the weight of the oxygen combined with the copper, or 0.4344 grams. Now using these two figures, the weight of the copper and the weight of the oxygen, we may calculate a rather accurate equivalent weight for copper, because we know that 1.7301 grams of copper was combined with 0.4344 grams of oxygen. And the equivalent weight is defined as the number of grams of copper combined with 8 grams of oxygen. So by using a rather simple proportion there, we calculate the equivalent weight of copper and find it to be 31.86 grams. This then is the value for the equivalent weight. Earlier, we saw that the equivalent weight times the valence equals the atomic weight. We've calculated the equivalent weight of copper from this experiment. Our value was 31.86 grams. We've also calculated an approximate atomic weight using the Dong and Petit method, and this approximate atomic weight was 67.4. If we multiply 31.86 by the valence, then we ought to get something approximating 67.4. We can solve this relationship for the valence. And we get 2.11. Now we know that the valence is always a whole number. And this calculation tells us that the valence of copper in this compound then is 2. Now we have to return to our original formula. We still know the accurate equivalent weight is 31.86 grams. We know now that the valence is 2. And multiplying these two accurately determined figures together should give us an accurate value for the atomic weight. This multiplication, when carried out, gives 63.72 as our value for the gram atomic weight of copper. Now, this experiment was not done with the utmost possible precision, and as a result, we have, as usual, introduced a small error. By consulting a table of atomic weights, we find that the recognized value for the atomic weight of copper is 63.57. Our determination, then, is a good check on the accepted value, differing by only 0.15. And this gives us an error of 0.15 divided by 63.57 times 100 of 0.2% of 1%. 0.23% is our error. And considering the inaccuracies attendant to this particular method, this is certainly not an excessive error. We've seen then how a chemist proceeds to calculate the atomic weight of an element from data which is readily available in the lab. He can get an approximate atomic weight using the Dong and Petit relationship. He can get an accurate equivalent weight by a method such as we employed today, the reduction of copper oxide. He can then determine a valence by using the two figures just mentioned, and with the valence and an accurate equivalent weight, he can calculate an accurate atomic weight.